I'm excited to kick off the first session on time domain astrophysics, which is quite a large field that basically studies everything perfect that evolves on, I'll stay here, on human timescales. And I'll try my best to talk both, once again, to the CS audience and the astronomy audience. I'll mainly focus on the open science questions, and then we will hear from Ben and Josh about methodologies that are being developed to address these questions. I'm so excited for LSST. It's going to be so amazing. And what I want to highlight here is that there's so much interesting time domain astrophysics that can happen. We're talking everything from the collisions of stars to supermassive black holes actively accreting gas and matter. And we're able to study all of these on human timescales of variability. My own field is supernova science, and so I'm just going to quickly emphasize what Phil's already said of how incredibly transformative LSST will be. I'm showing you briefly just a plot that is the discovery rate of supernovae as a function of year. So this is not cumulative, this is every year. For context, there's about supernova going off in our observable universe every 2 seconds. Of course, we can't see all of them. Most of them are too far away. And so what we're trying to do with incredible missions like LSST is to probe deeper into that universe to capture more volume, meaning more of these explosions. This is the story up till roughly now. Just look at the blue curve. What's really exciting is even though we've been exponentially increasing our discovery rate of supernovae every year, LSST breaks that exponential growth, and it's going to be a jump of 2 orders of magnitude in our discovery rate to 1 million explosions every year. And again, to emphasize what Phil said, those are hidden amongst the millions of alerts that we get nightly. So it really, within itself, is a needle in the haystack problem. The type of data modalities that we work with in astrophysics in this field are maybe threefold. First of all, we get these beautiful images from LSST directly. Those contain things like the host galaxy or the galaxy that supernova was born in. We also get we can extract from those images just how much photons are coming from one pixel as a function of time in different colored filters. And we call that time series, which is sparse and heteroscedastic. We call those light curves. Finally, for events that we think are really interesting and warrant further follow-up, we can take a spectrum, meaning I can break up its light into many wavelengths to really understand the elemental makeup of those high energy phenomena. That's an expensive task, so we do not do that for very many at all. I want to organize what I think are interesting scientific opportunities, but also challenges in terms of the 3 common anomalies that we typically work with. So I think everyone's familiar with these, and I'll go through the definition just in case. Point anomalies, contextual, and group or collective anomalies. When we say anomaly, and you don't study computer science or astrophysics, point anomalies are what you think of. They're things that just look weird. They don't look like exactly what we've seen before. To be more specific, what we often try to do is to build informative feature, which can be observed or engineered, or latent feature spaces that we summarize each of our different explosions or transients or variable stars into. Here is a goofy example. I'm just pretending that I see an explosion of a star, a supernova. I can measure how bright that thing is and how long it lasts. And we actually do see strong organization in that sort of feature space. And what's helpful about this is if I see a new point in a low density part of this feature space, I very naturally can guess that that's an anomaly and maybe interesting new physics. What's great about LSST is just by nature of having a million new phenomenon annually, then we can discover, in theory, 1 in a million level of rarity of astrophysics. Why that's so exciting is now we can really open up the floodgates to speculative ideas that we haven't observed yet. I very briefly will highlight 2 truly speculative ideas. Well, one is more so than the other. One idea, there's this huge open question right now of where do the most heavy elements come from, like the gold on your finger? We think that this comes from these ridiculous stars called neutron stars, and when they hit each other, they form these very heavy elements through the rapid neutron capture process. There's a big debate, though, that there might actually be a much younger origin here, maybe massive stars, particularly those that form black holes and these huge accretion disks around them can also form these heavy elements. A paper a few years ago, we developed exactly this sort of a very bold theoretical model, and we did predict it's about a 1 in a million type of LSST observation that we can only find if we really know what sort of features are unique about these sorts of explosions. A little less speculative, but will be challenging in LSST are the idea of population 3-star explosions, or what happens when the very first stars in the universe actually explode. These are challenging because they explode quickly, and that means that they should all be gone quite early in the universe, therefore too dim to see. It's possible, however, that there are pockets of these for the astronomers, low metallicity, so very old kind of dust that hasn't been enriched yet, that can allow these explosions to happen more locally. If we see one locally in LST, it has major implications, not just for understanding the first stars and their lives, but also for galaxy evolution and how those become homogenized or not so with cosmic time. We also, though, the more that we see new supernovae and explosions, the more that we are already seeing unexpected phenomenon that now we know is going to become common or easy to find in LSST. One thing that we've noticed most recently are these supernovae that don't seem to just explode as one kind of atomic bomb. They have multiple explosions. And what they're teaching us there is that stars are probably, all massive stars, are largely living pretty complicated lives with a partner, where they're exchanging mass, where they are driving each other's ending evolution, and we see kind of their final disagreements as this secondary explosion in time. And I'm showing here actually just an example. This guy's named 2023 ZKD. They all have nice names like that, that we actually just highlighted through an anomaly detection, fully machine learning algorithm as being particularly exotic. And we think the story that we are telling here is that we think what's happening is this guy, the star that exploded, has a black hole companion who is just ripping out mass from his partner right before death. So I think these are going to be notably more common, and it will really open up a new way to understand the end lives of stars in LSST. Okay, as a challenge, however, it's not the case, I think this is clear, that the feature set that we choose to try to find these anomalies is exactly correlated to the underlying physics, and that can be problematic. As a great example, in just the last 2 years, there was a new type of explosion discovered, and we have the weirdest naming convention that I'm not going to tell you. This is a 1EN type. What's important here to note is this star has been totally stripped of all of his outer layers all the way to his very inner core, and we've never seen something like that before. The way we know this is that we see these really interesting sulfur and silicon lines that get excited right after its death. However, the cautionary tale is that if I just took that same feature space I showed you, how bright I am, how long I last, this guy is not an anomaly, a point anomaly, by any means. He looks fairly typical, and only actually by going to a kind of model space were we able, well, I wasn't part of this, but were they able to point out that he seemed abnormal when compared physically to our understanding of typical supernovae. Okay, I'm going to skip my summary slides because we have one at the end. The next type, briefly, I'll bring up is a contextual anomaly. Here, what I mean is in the context of, let's see, there's two ways we can think about this. One is in the single modality, meaning this one type of data. So here, it's like an EKG or something. This is the example that comes up when you always Google this anomaly. But you can see that, so I have a heartbeat, or I can imagine, I don't know, like pulsar timing. And in this red, I don't have values that are out of the ordinary by any means. But in the context of the full time series, it seems that I have missed a beat. And so that does now flag as some anomalous behavior within the time series itself. A second type that I won't talk about as much is I can also think about multiple modalities where individually in each modality I don't stand out, but collectively then there's something quite odd that can pop out. But for this sort of context, I want to highlight the science that will be enabled by LSST for supermassive black holes, particularly those that are actively feeding on their local environment. These are called active galactic nuclei or quasars. Do not ask me why there's so many names. And What's so exciting is that LSST will discover somewhere between, depending on who you ask, 10 to 100 million of these sorts of events. And these have light curves that are always kind of stochastically vibrating on and off as they're slowly eating, munching on the food around them. Um, there's notably a lot of unexpected phenomenon that is incredibly challenging physically to model. We do not have a good physical forward model yet for AGN. Um, So, in particular, what I want to highlight is this recent discovery of so-called changing look AGN. So, AGN are very complex. They're these supermassive black holes. They're actively eating matter. They have these large torus around them, and what we used to think at least, is that depending on where we happen to be looking along this axis, so let's say we're looking down the jet, the AGN might look one way versus if we're along the plane another way. We used to classify these as things like type 1 versus type 2. However, we've recently noticed that actually, if we go back to an AGN, we take a spectrum 1 year, we come back a few years later, suddenly they can look as though they've grown a disk out of nowhere, or that we've weirdly changed the angle which we're looking at them. And that's not true. These things aren't toppling around on human timescales, that we're actually changing the angle. We think that these are very actively changing their geometry and their accretion in real time in a way that we could not have predicted before. So changing look AGN have the most kind of striking example of this, where they change type. They seem to completely grow or lose their torus in real time. These have, again, increasingly been discovered via just anomaly detection in time series, just like what LSST will be using. So here's an example recently from Paula Sanchez, who used a simple autoencoder to try to find these changing look in the time series themselves. Okay, so maybe that just sounds like, sometimes like weather, AGN weather to people. There's actually so much interesting science on the horizon for AGN if we could just understand how to have a physical forward model. One science case I really want to highlight is finding binaries of these things, two supermassive black holes that are circling one another and that actually are emitting a large amount of gravitational waves that would be detectable from pulsar timing or things like LISA. These are really hard to find, despite the fact that two things rotating around each other should just look like a sinusoid. The reason why is because the stochastic bubbling or murmuring of the AGN has correlated or red noise that we cannot easily forward model. I think what's so exciting, though, is that we can use data-driven models that are well-tuned to actually capture the physics, even if we do not have a full forward physical model in place, just due to the complexity of the problem itself. We can use those sorts of models to help us find anomalies like changing look AGN, or like AGN that have some sort of sinusoidal behavior that hints that they're actually in a binary system. Okay, and I think I have 2 minutes, so I will very briefly just say, the final type are collective anomalies. So here we can think of an example. I'm going to show the example of high energy physics first and then go back. So here, I like to think of this as more like null hypothesis testing. This idea that I have a helpful forward model that makes some prediction for what I should be observing. So here I'm showing you, the signal from LHC. And this is what they typically do to find physics beyond the standard model, is that they fully understand kind of the energy distribution they should be looking at in their beam, I think. And then they look for some anomaly on top of this null hypothesis or the standard model. We have our own examples. This is in astronomy. This is also not quite my field, but this is the Gaia sausage, where I think the name comes from this picture, basically, where if we look at the velocities of different stars in the Milky Way, thanks to the Gaia mission and its high precision of in its ability to do that, we actually see that, yeah, most of them seem to be doing what we think. They're going around the galactic center, but there is actually this weird sausage dispersion that we can see. And it turns out that this is, we think, the remnant of a former merger with a dwarf galaxy in our own Milky Way. And again, this shows up because it's collectively something that's atypical for the null hypothesis we had for how stars should evolve in our galactic potential. Within LSST, there are, again, many opportunities to find this. I think I'll just do my very forward-looking idea, which is that if we are to look towards kind of what high-energy physics is doing typically in this null hypothesis generation, I think one thing that's very inspiring is that they take these very complex systems, and from each of the runs of their collider, or in our example, for every time series we see in LSST, we can extract, again, these like just simple summary statistics. Here I'm showing a super famous one of an HR diagram that collects many different stellar types, and you can naturally see these sequences that, again, we have simple forward physical models to explain. What we can do here is to start looking for new clumps, looking for new collections that are not predicted by our physical models that now serve as important benchmarks, direct tests for those models. We've been doing this for a very long time with static observations of stars, and I think less so, but there's some greats in the audience who are thinking about these high-order summary statistics and families for variable stars. So here I'm color coding based on some of the variable types we see. But we still don't have these kind of full forward models to help us directly benchmark and test our studies. But I think framing this in an anomaly detection problem, that we can have collective anomalies that were unexplained, can really help us directly push on the physics that we are missing from variable star models for my field, for supernova science. But we need to make these high order, large scale predictions. Okay, so I think with that, I will just leave up my summary slide. And I don't know if I have time for two questions. Okay, thank you.
Thanks, Ashley. On the point anomaly, the example you showed that didn't, where the time series analysis did not actually indicate an anomaly, you mentioned that you did some physical modeling. Is that sort of, you fit the physical model and the parameters looked off? How did you do that?
Yeah. To be clear, didn't do it. But the team did, yeah. So yeah, exactly. So yes, so what they show is they show the picture I did, which is like, hey, if you just did the very naive thing of the most salient kind of hand-engineered features, this doesn't stick out whatsoever. But then what you can do is exactly, I can say there's only a few type of engines that drive these sorts core collapse supernovae, and I can just kind of click all of them in and go through all of them and ask, now in a conditioned way, if you were driven by radioactive decay, how abnormal would you be for the population? It stuck out. If you were driven by a magnetar decay, how abnormal would you be? It stuck out. Totally. So this, I think, was a great hint that that's a helpful way to look for anomalies.
But you do that test basically every single time, right? You do the physical model every single time, because otherwise, if you don't detect an anomaly the first time, you wouldn't do the follow-up analysis either.
Yes, you would have to have really fast inference, which would be great if SBI would work on this. Yeah.
Kind of related to that, the cadence of every 3 days might not be enough to capture the variability of many of these objects. I guess supernova maybe, but like our Lyrae are like half a day period. So is there a plan? I imagine with so many alerts, there would be a lot of competition for spots to go deeper into. And I wonder how that would be managed, or if you know anything about that.
Absolutely. That is, I will say, a can of worms. There are many ways to answer that question. Maybe I'll say a few things quickly. So one is that, the timescales are not well matched for incredibly rapid transients. For actually high periodicity, like you're at a high enough sampling rate that it's okay, that you should be able to find to phase fold if the period's significantly less than 3 days. But for things like transients, so they show up once, no, it's not well matched. We will have other ground-based facilities to help us that will have public data like LS4. But I think a lot of the fun new science will naturally lend itself to the longer-lived supernovae. And luckily for us, time dilation helps us there. If we are finding things deeper, then for some populations, they'll last longer naturally. For coordination, which is kind of the second part of your question, there's some coordination in the community, but it is very competitive, and I don't know how the landscape will change for us to compete for what we claim to be the most exciting science, because there'll be so much to do with LSST. Yeah.
Thank you.
Okay, let's thank Ashley again. And We will now have Ben Nachman, who is going to talk about the methodologies and the challenges associated with them. Go ahead, Ben.
Very good, thank you. Okay, so full disclosure, I'm not an astronomer by training, so I'm an interloper, but I'm learning as I go, and for sure, a lot of the techniques that are developed in different areas, including those in high energy physics that Ashley was pointing out, can be applied more generally. Okay, so I'm first going to present a few ways of I like to think about characterizing anomalies. There's many different axes, and these axes can be useful in identifying what are the different kinds of assumptions that are going into the models and how we might design tools to look for them. So one set of axes are the latency axis and the supervision axis. So latency axis here is how much time do I have to make a decision, basically. We've been talking a lot about transients, and transients can be fast, they can be slow, and what fast and slow mean is how long it takes to do follow-up, how long it takes to do an analysis. And there's also a stark division between things you can have to do online, that is, like say, in real time, and things that can be done offline, even if they're still need to be done quickly. So I'm going to be basically focusing entirely on offline, more or less here, and there's a whole suite of challenges that arise online that I'm happy to follow up at the end if there are questions. A lot of the methods that have been developed, especially those that are density-based, don't work online because of the YOLO nature. If you only get a look once, you can't do things like estimate densities, and that's an interesting challenge for these kind of tools. The other axis is the supervision axis, so that is I'll give a couple different ways of thinking about this in the next slides, but how much information I'm going to assume about the structure of the problem. And so unsupervised, I don't assume too much at all. I don't give any label information for the learning. And if you have supervised is the total extreme, and then somewhere in the middle there's noisy or partial label information that I can provide, and that is another interesting spectrum. Okay, another way of thinking about this problem is on these two different planes, which is how much model dependence am I going to put into the development of a tool. So there's two questions you need to ask every time you have an anomaly. The first one is like, is it weird? Okay, and how do I figure out if something is weird? And the other question you have to ask, which is often forgotten, is how weird is it? And so the first question, is it weird? When you think about how to find something that's weird, you first have to figure out, you will rely somewhat on what you think the normal stuff looks like, the background, and also what kind of things you're looking for, the signal. So classical searches for new things often will have, say, like a simulation or a stand-in for the background and the signal. You can train a model, classical or whatever, machine learning based, to distinguish them, and that's your kind of a normal approach. So it lives down in this bottom corner. But you could imagine other strategies where live in these other parts of the plane where you try to assume as little as possible about, say, what the anomalies look like or about what the background looks like. But then once you have an anomaly, you have to figure out how weird is it, especially because we're often looking for statistical anomalies. No individual example is anomalous, and so I need to be able to figure out how anomalous it is by looking at the context. And the context can also depend on what the model of the signal is and what the model of the background is. So for the signal, maybe you have to know something about like how often it happens, and that will help determine how you would figure out how anomalous it is. Okay, my third picture here, which is Ashley touched on a little bit, is different kinds of anomaly, or point anomalies versus group anomalies. I'm going to put all the non-point anomalies into group anomalies, but more or less, the point anomaly, as you see a single example, you show it to an expert, it's an anomaly, Nobel Prize. Okay, that's like kind of how it works, and we almost always are never in that case. Sometimes we get lucky, like when the positron was discovered 100 years ago, that's more or less how it happened. There was a charged particle going through a plate and it was bending the wrong way, and okay, boom, Nobel Prize. But that usually doesn't happen. Usually it's a group anomaly where there might be, say, like in this picture here, instead of a flying pig, there's a few more pigs than usual at the barn, and I have to know the distribution of pigs to know it is weird, okay? And that's a much harder problem, but that's why it's an interesting problem. Okay. So now let me drill down a little bit, thinking about some more, dissecting this a little bit. So on the supervision axis, there are many different strategies, and the strategies are often connected to what you're assuming about the new stuff will look like. So these are the unsupervised, weakly supervised, semi-supervised, supervised. This is all about label. So what information I'm going to teach the model as it tries to look for some new structure in our data. The weakly supervised, semi-supervised, I would say is not, whether it's noisy, partial labels, somewhere in between, there's a whole spectrum of tools, and not everyone agrees on the nomenclature. Okay, So unsupervised, really here I have no labels, and typically the goal of methods developed to do unsupervised anomaly detection are looking for events or objects that have a low likelihood. So underneath the null hypothesis, the background only hypothesis, you have some density and they have a low probability of being like the background. And there are a number of different strategies for doing this. I think Ashley mentioned in her last talk that someone used an autoencoder. So autoencoders are of this class. And an autoencoder, for example, like the one shown here, is you try to automatically compress and uncompress the data. So imagine you have image-like data, you can learn to compress and uncompress at the same time. And when you take some new data set, some new point you haven't seen before, you compress and uncompress it. If it's not uncompressed very well, so the original and the compressed, uncompressed look very similar, then likely it has a low density. That's because your compression algorithm should be spending most of its its bandwidth on things that are common. That's how compression algorithms work. And so things that are rare, it should not do a very good job at those. So that's sort of an indirect way of probing the density, but you can also probe the density directly by training, say, normalizing flow, which is an algorithm that tries to model the actual probability density of the data, and you can use a normalizing flow, for example, to also find anomalies. Okay, that's unsupervised. There's a whole class of algorithms that I'm just going to call them weakly supervised, where you have noisy labels. And here, one set of these kind of tools are cases where, say, you have two sets of events or objects. And one of them might be signal enriched, one of them might be signal depleted. I mean, we're never in this situation where you have lots of signal, right? It's an anomaly, so like they're both almost all noise, and then a little bit of signal maybe. But having these two samples to play off each other, you can think of them as having noisy labels in the sense that the signal enriched is like noisy label signal, and the background is like noisy label background, and you can play them off each other to find something new. Okay. So that's just two examples, and I want to focus on these two because it's interesting to see the trade-offs between the two approaches. So for, first of all, there's the anomaly assumption. So for the unsupervised methods, we're assuming that the anomaly, if it exists, is rare. And for these weakly supervised methods, for example, let's say you want to train a classifier to distinguish these two data sets, you're assuming that you have two data sets for which the signal, if it exists, is more prevalent in one than the other. So it's overdense. And there are many different assumptions that go into these different tools, but from a statistical point of view, the main drawback, from my perspective, of unsupervised methods is that it depends on, rare is not universal. So if I change my coordinates, rare can change. So that's a key challenge. I mean, forget about even picking the features. If you just have the same feature set and just rotate it, you get different rare. Well, rotating won't work as linear transformation, but nonlinear transformation, you'll get a different set of anomalies. And for weakly supervised, you need the two samples. So it's not always possible to construct a reference either from data or from simulations. Okay. So just super quick a note about coordinates, because unsupervised anomaly detection, like with autoencoders, are extremely popular. So I just wanted to, I think it's not always appreciated. This is a feature of them. So this is like a super trivial example. Let's say you have two Gaussians. If I apply linear transformation to the Gaussians, like on the top left, say like my x are my Gaussians, and I apply 2x plus 5. Okay, so I just moves them around. That doesn't do anything. What's anomalous is still anomalous. Because it's a linear transformation. But if I say do e to the minus x, so it's a nonlinear transformation, I swap where things are, and the tail that was on the right is now kind of in the core of the distribution for the yellow guy. And so even if you could get the exact density, which autoencoders do not do, and there's all sorts of questions about autoencoders versus variational autoencoders and whether it's learning the density or not. In this case, you have to be careful about how you pick your coordinates. Okay, and I just have, this is one slide just to compare, let's say, unsupervised versus weakly supervised. So say you have the left picture here, say it's Gaussians, right? So I have two Gaussians, and there are three different colors, and the different colors correspond to different transformations of the Gaussians. So there's the solid lines, the three colors are different methods, the different kinds of lines are different transformations. So the solid lines are Gaussians, then the dashed lines, I apply the inverse CDF of a Gaussian, so it makes a Gaussian look like uniform distribution. And then the dot dash is I apply a tan H, so it's another nonlinear transformation. And then there's the red is a normalizing flow, the green is an autoencoder, vanilla autoencoder, and the purple is weakly supervised, and where I happen to have a reference. Okay, and so the purple lines, they all look exactly the same because likelihood ratios are invariant under coordinate transformations. So that's a benefit of doing likelihood ratios. It doesn't depend on the coordinates. They're exactly the same. And for the other ones, you can see that, first of all, their performance is less, because for unsupervised learning, I'm not telling it anything. So if it's good at finding something, it's just basically by luck. And they vary depending on the coordinates. So that's an interesting challenge that unsupervised methods face, is that there isn't like a limit in which they're optimal, and they suffer from this choice of coordinates. On the other hand, the right picture here is another example of this anomaly detection, where in this case it's from a collider physics example where we're comparing as a function of the strength of the anomaly. So how many anomalous examples there are. And the thing about unsupervised learning is it doesn't actually care, because you're not asking how much signal is in this data set, you're asking what looks like not the background, basically. And so it doesn't care how much signal you have in your data set. Its performance is independent of how much signal you have. So that's a benefit if the signal is very rare. Whereas some of these other methods that like use the presence of the signal to find the signal, they do very bad when there isn't that much signal, and they do very good when there's a lot of signal. And so that's why you see this kind of crossover point between unsupervised and weakly supervised. Okay, and this is AUC, and it's not the full story. You could ask the question, does that orange value, asymptote of the orange value, is it a useful amount of power or not? And it depends on the context. Okay. Okay, so now what I'm going to do is show a worked example from astrophysics using stellar streams. So this is going to be in the context of a resonant anomaly. So resonant anomalies are kind of a subclass of, it's a group anomaly, it's a subclass of these weakly supervised methods can be deployed to them, where you have some dimension. Here I have m. You can tell I'm a collider physicist because the m is the invariant mass. But here it could be time, it could be many other things. And so whatever, if the anomaly exists, it's localized somewhere, and then the background of it is just featureless. Okay, and then the idea is I need to generate noisy labels. So I could create a region near where the anomaly is, and then a region away from where the anomaly might be. That will give me my noisy labels, and then from there I can use other features, whatever other features are available, say spectra or positions in the sky or whatever else, to try to find the weird stuff. And in the context of stellar streams, here's some pictures of some stellar streams. It might be, so because all the streams are basically the remnants of protogalaxies, because all the stars in the stream came from the same protogalaxy, they're moving with roughly the same proper motion. So proper motion is like a resonant feature. So in that sense, I'm looking for an overdensity in proper motion of stars that kind of look similar otherwise. And so the other dimensions that I can use would be like the location in the sky, metallicity, all those kind of things. And so this is like the example I'm going to give. All right. And so this mu here is the proper motion. The background stars on the left in one particular patch of the sky it's featureless. It's kind of smooth, and you can imagine constructing a signal region and a sideband region away from there. And the stream stars in this particular case for this simulated stream, they're localized. And so just using this one dimension alone, you could try to find something that's overdense. But you can also use the presence of other features. In this case, this is from the Gaia data set, so there's many dimensions. And you can use those to try to tease out additional events. Okay, so for example, if you look at GD1 is a particularly nice bright stream in the sky. And these kind of machine learning methods, they work. They can automatically identify the presence of the stream and the stream stars. I didn't tell it anything. All I told it was look in this particular patch. And this is sort of complementary to all the existing methods for finding streams, which rely a lot on astrophysics, which is great because we know a lot about astrophysics. But if you want to look for things that go beyond the assumptions that are built on the astrophysics, then these kind of tools can augment those strategies. So here, this is just highlighting that basically the machine learning method finds all the same physical features that the classical method finds, so these like gaps and spurs and other properties of the stream. But you can also imagine going beyond that. So you can see that the stream found by machine learning is not as regular looking. That's because it doesn't just draw a big box in some high-dimensional space. And that might be useful for understanding structure that goes beyond the assumptions that were in the classical method. And some of my friends, I wasn't part of this paper, but basically took this and scaled it up to the full sky. And have found a number of interesting stream candidates. These are some pictures of stream candidates that merit follow-up to see if they're really streams or not, using this automated method, or methods like this, to look for overdensities in this high-dimensional space. Okay. So yeah, the left picture is the location in the sky, and the right picture is this, in the proper motion. In addition to finding the streams, we can also use these tools to identify new properties of the streams themselves. So, for example, we found in GD1 a number of stars that look like they're consistent with the stream, but they're not labeled by the classical catalogs of GD1. And so that merits further follow-up, and maybe that will allow us to learn more about the structure of these streams going forward. All right, the last slide of content is This is now some ongoing work to think about how we might try to integrate more model dependence. So everything I've said so far basically ignored everything about astrophysics except for knowing that they're localized in proper motion. So now if you had a bunch of simulated streams, for example, how would you incorporate that into the learning task? So in this particular case, we have like 100 mock streams, and we could train, say, a supervised model. Like the simplest thing to do is to train a supervised model on all the streams, just all at once. In this case, it's a big graph neural network on all the points inside all the stars inside the stream. And that's the red line here, has some performance on some holdout set of streams. And the blue line here is if you do this weakly supervised method, so I don't know anything about astrophysics. All I have to say is localized somewhere. And the x-axis is how much of the stars I randomly throw away. Because I want to say, as I mentioned for these weakly supervised methods, if you throw away stars, it does worse. If you have all the stars, it does better. And there's like an interesting crossover point. And that actually depends on which streams you're looking at, and there's kind of a trade-off between the kinds of modality. Like if the streams you're looking for look more like the ones you trained on, obviously they'll be better at finding them. And so there's interesting trade-off between imposing more information or not in building these tools. Okay. I've only scratched the surface of what's possible, and it's really exciting to see science start coming from these tools to automatically find new structure. We definitely need new R&D in addition to adapting tools for astrophysics and also thinking about, I'm really excited about time domain astronomy. I've so far focused not on time domain, but time is an interesting dimension for making things resonant. So a lot of these tools basically should just apply. And I think it's also exciting to think about developing data sets that can be used for benchmarking and testing these kind of tools. As a small plug, we actually have a NeurIPS challenge, a cosmology challenge this year for which anomaly detection will be an interesting component, and happy to say more about that later. I think that's it. Thanks.
Thank you, Ben. Questions. We have time for 2 questions.
So you mentioned that when there were these stars that one stream finding method identified as part of the streams and another one didn't, that they would be interesting targets for follow-up. And I was wondering if you could say a little bit more about what sort of follow-up would resolve that discrepancy.
Yeah, so we, in this, let me see if I can go back to that. Yeah, here, for example. Yeah, so we published just like a list of whatever the neural networks that are the most anomalous, are the most likely to belong to the stream. And this, from the Gaia data set, for example, they have limited spectral information, so you could try to get a spectrum. And I'm not an astronomer, but I'm told that will help distinguish if they belong to a stream or not. And maybe someone who knows more can tell me if that's true.
I just wonder if you could say more about where you think the most exciting methodological development is in this space, and what role new time domain data might play in that.
Definitely. I mean, for sure, a lot of the development in industry has been on point anomalies, because for a lot of industrial processes and other things, that's what you care about. And we almost never care about that case. And so, but a lot of anomaly detection has been applying those tools to these problems. So like autoencoders and other tools, which are very powerful, but there's a whole, their power is limited, basically, for the reasons I've tried to stress in this presentation. So I think, especially for time domain astronomy, where you have this context from the stuff, it's transient. That's exactly the opportunity to develop new methods or adapt methods that can use this reference information from the sideband in order to do better anomaly detection. And so I think that's going to be quite exciting.
Okay, let's thank Ben again. And our last invited speaker is Josh Bloom from UC Berkeley, who is going to ask tough questions about the applications of these methodologies to time domain data.
Well, thanks, everyone. So I think it should be obvious by now that the onus on astronomers when working with data in the context of anomalies is not for us to write papers about how to find anomalies, but to actually find them and then show that the physics of the objects that we are identifying as anomalous from the data are actually different than some common objects that we already know about. And so it's beyond the methodology. And when we actually go from applying these methodologies to data, you wind up seeing just how absolutely hard it is to be working in the anomaly space in astronomy. So my talk hopefully will give some context to that. This is one of the ways that we can think about the explosive universe in the time domain. On the x-axis is time, on the y-axis is terrible astronomer units for brightness. And the stuff in the middle, type 1a supernovae, type 2p supernovae, very common. You heard from Ashley, once every second or two in the universe, these things happen. They're very interesting for some types of astrophysics. People have made a cottage industry out of finding these things and studying these things, but they're very boring because they happen all the time. This is the haystack that people talk about when they say we're going to classify the haystack of transients so that we can get rid of it and look for all the needles. One way to think about those needles is physically driven models and theories of interesting objects that we haven't seen yet. This slide was made before 2017 when the actual first kilonovae were identified in this very short and very faint transient. Neutron star mergers produce this little blip of light. But these other things that you see up here are theoretical, have not yet been identified. And it's pretty clear based on just the light curves alone that when they happen, they're going to hit you over the head, right? So if we're able to build filters against the things we already know about, when these things happen, if they even happen in nature, we will find them. By definition, in the Rumsfeldian sense, what we don't know and haven't thought about, we can't even put up on this slide, but that is the sort of underlying current of the things that people are thinking about when they are trying to work in the anomaly space. More commonly found, and this is what Ashley alluded to and things like the changing look AGN, is that what happens is we see these light curves. They look very similar to objects that we've already seen before, but then when we get follow-up data at other wavelengths or we take spectra, we wind up noticing that they're actually somewhat different. And then upon lots of digging, wind up realizing that there's new physics. Some examples of new subclasses, we think things look like gamma ray bursts, but then if you dig in a little bit more and get some other data, they appear to be something completely different in terms of their origins. Relativistic tidal disruption events for the astronomers in the room, maybe one example of that. And then there's also, other types of weird supernovae that look one way in their spectra early on, and then they transition into another type of spectra. And there's lots of different types of examples of that. But what's very clear is that for us to have a full, complete picture of the physics of these anomalies, we often need to get follow-up that doesn't just come from one telescope in a few bands, but we need to get this at multiple wavelengths, and we need multimodal observations to be able to truly understand if we are looking at something novel. So in my group, we've been working with multimodal foundation models for a lot of different reasons, but I'm going to index here on what we've been able to do in the context of anomalies. This is a bit of a complex slide, but the idea is that we have a bunch of different modes. So we've got time series, we've got spectra, we've got metadata. They each have their own encoding. And then through a contrastive learning process, we wind up comparing these different modes to each other and wind up kind of forcing the embedding spaces of all these to be the same, which allows us, as we learn on a very large unsupervised data set, to be able to build up this kind of representation, a learned representation across all these different modes to give us a more holistic view of these different objects. And then when you compress this, 512 dimensional space just for visualization purposes, not for analysis purposes, into 2 dimensions using something like UMAP, you wind up seeing very naturally, even though we didn't give the different classes of these objects to the learning process, they very naturally wind up clustering based on their actual known or believed to be classes. And what's kind of exciting here is not only are we getting that kind of clustering very naturally, so we're effectively learning in the representation space that there are these different clusters, is that we have found, somewhat surprisingly to us, there were 2 different clusters just in this 2-dimensional space of Mira variables, even though in the original training data, These were only labeled as just miras. But then upon inspection, we saw that those two different clusters very naturally, spectroscopically split up to two known subclusters of miras. So this is kind of a nice demonstration that in a very unsupervised way, and just even visually going in, not even with clustering methods, we can go in and sort of start finding some really interesting new subclasses. So that's kind of a nice demonstration of that. But what's also kind of interesting is that we can look for those point anomalies in places where, for instance, we have an object that shows up in an embedding space that's not where it's supposed to be according to these learned representations. And these could be objects that are incorrectly classified. Usually it's because they have things like their periods are wrong, or actually the classification catalog that we used itself was wrong in a few cases. Or we have things that are actually correctly classified, but they're weird, maybe in one of the modes. And so we have examples of those, of what we call like in-class outliers, where we have kind of normal looking light curve in a eclipsing binary system, but then we have something anomalous where we have a whopping a line there that's usually not there in most eclipsing systems. There's some sort of accretion disk process. This has X-ray associated with it, which was not part of the original data. And this is kind of a known subclass of detached eclipsing binaries that are transferring mass and producing these X-ray lines. So that's kind of a nice proof of concept as well. But the thing we got really excited about is because we have this embedding space, we can do searches in, let's say, cosine distance of everything to everything else. And we wound up seeing this really interesting stellar-like spectrum with a massive absorption line right here. And I got really excited about this because I had no idea how to do this physically. And we got really, really into the idea that this may be some sort of interesting accretion disk. And then we wound up querying to find other objects in just the spectral dimension that looked like it. And there were 10 or 20 or 30 of these things, all with different light curves. And we wound up concluding in the end that what we had was a bad spectral reduction. And so, before we wrote the Nature paper, for those that remember this movie, instead of bad dates, it's just bad data. And so the anomaly detection worked. That's a good thing. The problem is it wound up showing us some bad stuff in the data. And this is in a very large data set. I don't know what went wrong in that reduction, but this is going to happen. This is going to happen a lot. And it kind of, makes sense that we should start thinking about other ways to be finding these anomalies, in part because as you start thinking about the cursive dimensionality, when we have these large dimensional representation spaces, which we kind of need to do when we're looking at these complex physical objects, we're not just looking at 4 or 5 numbers that can adequately represent one of these modes. We're going to need dozens, maybe even hundreds. In that context, the distance between the nearest points in a very large dimensional space winds up getting large, but the difference between the distance of the largest distance and the smallest one is actually getting smaller and smaller. And so what this says is that over time, in these representation spaces, if they have to be large to describe the data, one of the challenges that we have is that it's just going to be harder and harder using clustering techniques to find these outliers. And so one idea is to use not the representation space, but use the representation alongside classification to be able to come up with distance metrics. This is something we developed in 2012, actually, in the context of random forest, but it can be done with other types of learned representations, where very simply we're just asking, at least in this context, as we have a new object and we query a new object that's unlabeled, where does it show up in all of the different trees in the random forest relative to other types of objects? It's different than isolation forest because it makes good use of the classification. This avoids these kind of distance approaches in the feature space, and it is semi-supervised in that it learns from the actual labels. So we're actually sort of imbuing some of our knowledge of the physics of the systems that we're looking at to be able to get this distance metric. And this also worked. And we had a undergrad in 2012 looking at our best anomalies, and she found this amazing object which looks kind of like a Cepheid that's extremely long period, 250 days. And we had papers, or we had emails back and forth saying, well, should we call Leslie Sage at Nature? Is this something that we should get excited about? Adam Miller, my student, said, this looks like a Cepheid, but the period is way too long. And it turns out there were a bunch of these things in our data set. We got super excited. And then we're like, we should probably look at the images. And indeed, there's like a big red mirror right in the middle there. But then we realized the photometry we had was from a large aperture, and what was happening is these mirror variables, which are largely sinusoidal, go up and down. When they went too far below, the light from these other two stars here basically dominated inside the aperture. And so we found an amazing set of anomalies. It just turns out it was bad data. So you see the theme here. Importantly to emphasize is that domain experts had to be in the real-time loop before we actually started going farther down the road. And it's that kind of imprecise and bad data that you didn't usually take yourself, but somebody else took for you and put in a database, that becomes a major bugaboo as we try to actually find new physics. And so if we're cursed by dimensionality, we're really damned when we have real data, right? So if we're getting just to the edges of our very large dimensional volume, very naturally, if we now have noise and improperly characterized noise, we're going to always find these objects that are beyond the edges of what we've already seen before. And this is a real problem for us. I think Tolstoy said it best, all data anomalies are anomalous in their own way. And for those that have looked at amazingly important events, there was a massive glitch right as the most important gravitational wave event of our life happened. Find guidance sensor on Hubble fails sometimes and produces beautiful images. And then, unfortunately, we have to contend with satellites that streak through our images. When you look at data, you find a lot of anomalies. And so the question now is, can we start thinking about embracing anomaly detection to operate our telescopes better and produce better quality data downstream for the end users? And so maybe we should be thinking not so much about anomalies on this sort of final resting place of data that's been carefully curated for us in databases, but doing it upstream, running it on the telemetry of logs from these telescopes, running it on raw science images to catch those kind of weirdos, and to find the distribution shifts that those that are running these large facilities can identify before they wind up putting it into a database and cause people to write papers they shouldn't be writing. So it should also be clear in just the last minute or two that I have that we don't really care about anomalies. What we care about is uncovering new physics, and anomalies are just really a stepping stone, a means to an end. And so if we think about using algorithms on large databases to find anomalies, what we should be thinking about that is as a stepping stone in a much larger data flow, where we can do maybe a better job upstream. But downstream from that, we might also be thinking about ways that we can help ourselves and protect ourselves against going down some path. So how do we automate sort of novel physical insight on this kind of autonomous scoring that we're going to be building? Well, one could be to build in these physical gut checks. So we know there's things like brightness temperature limits and Eddington limits and things like that. So maybe we have some crude physics that we fit to all of our anomalies, or maybe we build models with inductive bias from the beginning, so our representations don't allow us to go off into La La Land, or maybe we use simulation-based inference on some of these things where we have good physical models that are expensive to run on lots of data, but we can do it in a surrogate, quick way. So that's where we should be now. We're getting to the point in LLMs where maybe we're going to start asking, agentic Occam's razor questions like, here's some class of objects that I'm excited about. Can you go off and look at the literature for me and tell me what these things might be more mundane or otherwise? I'm assuming that there's something wrong with the data, but let's figure it out. Rank order the ones that might actually be truly physical. This could be one of the filtering techniques that we'll get to very quickly. And then, way out into the distant future, like in 2027, we're probably going to be in this world where this is the query that we all learn as grad students. Please develop a plausible physical model using MHD, nuclear astrophysics, GR, that explains all the data we have on this collection of sources. What other data should we get to test that theory? And by the way, just go get the data. So with that, I'll put up my summary and happy to take questions.
Josh, I liked your curse of dimensionality slide. Is there a way to work around that with dimension reduction followed by nearest neighbor and tessellation methods?
It is a good question. I think the way we have been working around it and why anomaly detection has actually been doing okay is because some of the things that we look at and we care about en masse can actually be reduced down to just a few dimensions, or then we're only working in 10 or 20 or 30 dimensions. But my supposition here is that as we start kind of knocking off most of the objects that we're going to be seeing in LSST Rubin, for instance, we're going to have to get to more and more subtle physics, which means for us to create distinguishing characteristics, distinguishing representations, we're going to naturally be forced to have larger numbers of dimensions. But yeah, for sure, we should be thinking about creating sparsity and like rewarding sparsity even at the loss function level in the creation of our representations. Because we just picked 512 for our thing, but maybe we would have done just fine with 128, and then you start being able to do better and better with clustering.
Okay, last question.
Hi, I have a question regarding the anomaly definition. I just wonder whether because of these many variables, and we could end up with, for each, just pick one star from the sky, and then I can find a definition, make it weird, and with this a concern of how we can avoid this situation.
Yeah, I mean, I think that gets to that dimensionality problem, right? Is that, everyone in this room is like the most amazing person in the universe in some axis, and, let's pick that axis very, very carefully. And yet at the same time, we all can be well characterized by a smaller number of parameters and approximated, not with an LLM, but like, something that's kind of finite with a finite number of bits. So it is a problem. It gets to that dimensionality issue, but fundamentally, in the end, it gets to whether that star represents new physics, right? And yes, that star is going to be weird in some very, very special way, but does that matter? Right? And does that matter question gets to, does it represent physics that we think is fundamentally different or an improvement upon the physics that we already know? And for most of the cases, the answer is going to be no, it doesn't. It's just sort of a stochastic implementation of something that we already know, those processes. And so that is, you're kind of hinting at one of the biggest challenges is that if everything can be anomalous if we slice it the right way, then how do we ensure that if it truly is anomalous, it also maps to truly new physics?
Okay, let's thank Josh again. Okay, now we have the fun part. We have a discussion in our tables. We've heard a lot of very interesting questions and challenges raised regarding time domain astronomy and anomaly detection. We will take the next 25 minutes to discuss within our tables. The good thing is that we have a very large variety of people coming from different places. So it would be a good opportunity for you to sort of understand what are the questions that people from other disciplines ask in that context. And once you have some discussion points that you think are worthy for the report back for after the short talks and the break, please write them down on your on the post-it notes with the table number and put them into our generalized hat that sits there on the whiteboard. And finally, I will kindly ask our invited speakers to disperse between the tables. Risa, there is...
Yeah, just if you're sitting in the back, join a table. Don't be shy.